All right, more with exponential applications. The United States stamp was valued at 4 cents in 1962, and it was valued at 49 cents in 2014. Use this information to write an exponential model for the value of a stamp. So, 4 cents, 0.04 is P naught. That is our initial value, okay? And 1962 is T equals 0, okay? So, now we have P of T is 0.49, right? It's 49 cents. That's our current value based on this model. When T is equal to how much? Okay, so we're going to take 2014 minus 1962, and we get 52 years. So T equals 52. So that is true when T equals 52. Cool. So let's take our model. Our model says P of T equals P naught e to the kt. What do we know? And before we go on, why are we using this model? We're using this model because the price of a stamp is unbounded. It is unbounded. It could keep going up and up and up and up and up. There's no reason that it couldn't, okay? And that's common with financial applications. So, what do we know? We know the current value is 0.49. We know the initial value for the scenario we were given was 4 cents, 0.04. E, and I don't know K, and I know T is 52. Okay, so the only unknown is K. What do we need to do? We need to isolate this exponential expression. So the first thing I'm going to do is divide by 0.04. Divide by 0.04. Okay, now when I do that, I'm going to get, let's grab the old pocket brain, 0.49 divided by 0.04, okay? That's going to be 12.25, 12.25, and this goes away, we get E, and you can rewrite this as 52K if you want to, put that coefficient out front. So we get 12.25 equals e to the 52k. Now, we want to get rid of this exponential expression. To get rid of an exponential expression, you use a logarithm. Since this is an e, we're going to use log base e, which is natural log. So take the natural log of both sides. This guy comes down as a multiplier, so I'll write this out. It's 52k times natural log of e. Natural log of e is 1. Okay, so you're left with 52k on that side. And then the natural log of 12.25. So this becomes, natural log of 1225 is 2.5055. And I'm going to just put dot, dot, dot. There's a whole bunch more. I'll let you see. I mean, it's a whole bunch of numbers. But we'll just keep it that way. And that's equal to 52k. Now, divide both sides by 52. So with that number still on my calculator, I'm going to divide by 52, and I get k equals 0.04818, and it just keeps going. And you're going to pick a spot to round. They're going to tell you to round to, 2, 3, 4 decimal places. So I'm going to go ahead and round this to 4 decimal places. Okay? I'm going to round this to 4 decimal places. So 1, 2, 3, 4, and that 8's going to make that a 2. So here's my model. My model is P of T equals 0.04 e to the 0.0482 t. Okay, so that is the answer to this question. There is my exponential model. And then they want me to use this model to predict the value of a stamp in 2020. Okay, so 1962 was T0. So 2020 minus 1962, this is T equals 58. That's what they're asking. What's the value of a stamp when T equals 58? So I take my model and I say P of T equals 0.04 e to the 0.0482 times 58. And literally, we're just going to type this in. So I'll put my calculator where you can see it, hopefully. See if I can get it to show up in the light that I've got. And I'm going to take 0.04 times E, right? So it's above the ln key. Make sure you got your parentheses, 0.0482 times 58. Press enter. And I get 0.65489. Now, this is money. The value of a stamp is money. I have to round to 2 decimal places because it's money. So I'll look to the right of this 5 as a 4. We're going to round this down. So that's going to be 65 cents. Okay, so P of T is $0.65 or 65 cents. Okay, so there's our model used to predict the value of a stamp in 2020. Thankfully, stamps actually cost a little less than that in 2020. Okay, so find the growth rate of the U.S. postage stamp using your model. Okay, find the growth rate of the U.S. postage stamp using your model. Okay, so and the way this is worded, it didn't come across right. But what they want you to find is find the growth rate model of the U.S. postage stamp using your model. Okay, what are they asking us for? What are they asking us for? They're asking us for the derivative. Let me flip back. They're asking us for the derivative of this guy, okay? They're asking for the derivative of this model. We haven't covered that yet, so if we wanted to know that derivative of that model, that's going to come later on in this class, okay? So, but we are going to do that. We are going to do that, so that may come back later on. So you guys who are watching this, that's going to come up later, okay? What if they just ask for the growth rate, as this states? Well, what is the growth rate? Well, our model, let me copy it down. Our model was 0.04, so P of T equals 0.04 E to the 0.0482 T. So what is our growth rate? Growth rate. What is our growth rate? Well, K is our growth rate. So this is going to be 4.82%. That's our growth rate. Okay, so it's going to be given as a percent basically. So we just take this guy and move the decimal 2 places. Okay, cool. So a lake is stocked with 400 rainbow trout. The size of the lake and the food supply limit the growth of the number of fish to 2,500. Population is given by the equation P of T equals, and there's your equation. Find the number of trout after 5 months, 10 months, 20 months. So what are they asking us to do? What are they asking us to do? They are asking us to find the number of trout after 5 months, 10 months, 20 months. So all they're asking us to do is to plug in 5, 10, and 20 for T. Okay? So T equals 5, T equals 10, and T equals 20. And what they want to see from us, right? What they want to find from us or see from us is, goodness gracious, I'm dropping stuff. They want to see, can we plug this in and find, okay? So here goes. Let's take this model. So P of 5, right, when T equals 5 would be 2,500 over 1 plus 5.25 E to the negative 0.32 times 5. Now, the way I like to do these problems is I like to go ahead and work the bottom. Okay, so I'm going to say 5.25 times E to the negative 0.32 times 5. And then I'm going to add 1 to that. And I get 2.05995.6. And there's more, but that's plenty. And then I'm going to take 2,500 and divide it by that number. And I get 1,214 trout when I run that number. Okay? Fair enough? Cool. So then we're going to do the same thing for 10, right? So this P of 10 is going to be 2,500 over 1 plus 5.25 e to the negative 0.32 times 10, right? So that'll be 2,500 divided by, let's find that number. So that'll be 5.25 times e to the negative 0.32 times 10 plus 1. And I get 1.214001571. Okay, so I get all that. So 2,500 divided by that number gives me 2,059 trout. Okay, so what do we notice? We stocked 400 trout, 5 months they've grown, 10 months they've grown. Let's see what happens at 20 months. Okay, see what happens at 20 months. So P of 20, right, will be 2,500 over, and it's pretty much very repetitive, guys. 1 plus 5.25 e to the negative 0.32 times 20. So P of 20 equals, and let's see what this bottom number gives me. I'm actually going to type it in where you can see it this time so that you can kind of see what I'm typing here. So I'm going to take 5.25 times e to the negative 0.32 times 20. I'm going to press enter, right? And I get scientific notation this time. And you got to remember that minus 3 just means to move the decimal 3 places to the left. So if one place puts it there, and the next 2 will add zeros. So this will be 0.00. Oh, wait, I forgot. I got to add a 1 to that, don't I? So plus 1. Don't forget to add that 1. So it'll be 1.008723176, something like that. Now, if I take that 2,500 and divide it by my previous answer, this 1.087, I get 2478. All right, if I 0.3, I round that down. And what do we see? We're getting really close to that limit of 2,500. And if we went to 30 months, we'd see a few more fish, but pretty much we'd hang right around that 2,500 number from here. Okay, so that's a limited growth model. What do we see? We see from time 0 to 5 months, huge growth, 1,200 fish, huge growth. And then from time 5 months to 10 months, we see 600 new fish. And then from 10 months to 21 months, we see 400 new fish. Why? Because we're hitting that limiting number. Okay. So then, find the rate of change of the trout population. And again, K is always going to be this guy here. So what is the rate of change of the trout population? It's going to be what? 32%. 32%, right? 0.32, 32%. Okay, that's it. Okay, now that is exponential applications. Next up is we're going to talk about derivatives of exponential functions. Okay, so when we talk about the rate of change, it's not going to be a number, it's going to be a function. So that's what's coming up next. If you have questions, leave them in the comments or email me.